Once we've got the basic rules down, then we can take derivatives of combinations of those functions. Let's just look at some examples where we can put all this stuff together. So this problem asks you to take the derivative with respect to x of the arctangent divided by the natural log. So we want to take the derivative with respect to x of this. Of course, the first thing we see is that we're dealing with a quotient. So for a quotient, you take the derivative of the top times the bottom minus the top, which is the arctan in this case, times the derivative of the bottom all over the bottom squared. So the natural log of x all squared. And then we just follow the rules that we had. The derivative of the arctan is 1 over 1 plus x squared times the natural log of x minus the arctan of x. The derivative of the natural log is 1 over x all over the natural log squared. At this point, the calculus is over. We've found the derivative, but it's not in the nicest of forms, so we'd probably at least like to get rid of these tiny fractions within the larger fraction. When you have these tiny fractions inside a bigger fraction, they're called complex fractions, and the best trick for getting rid of those is to multiply top and bottom by something that the tiny denominators can go into. This denominator could go into x, so I'll multiply top and bottom by x. This denominator would go into something that had a 1 plus x squared in it, so I'll multiply the top and bottom by 1 plus x squared as well. So when I use the distributive property then, when x times 1 plus x squared hits this 1 over 1 plus x squared, we just get the 1 plus x cancels and we get x ln x minus the arctangent of x. When 1 over x hits x times 1 plus x squared, then the x's cancel, and so we have the arctangent times 1 plus x squared all over. Let's see, we've got the natural log of x, that whole thing is squared, and then we've got x, and then we've got 1 plus x squared. Not the prettiest thing, but at least we got rid of that complex fraction. Let's do another. Okay, we're asked to find the derivative of this function. We've got really one function inside another function inside another function. So we've got x squared plus 1. I know take the derivative of that, but that's inside a secant. I know take the derivative of the secant, and that's inside the tangent. I know take the derivative of the tangent. So let's do that then. If we want to take the derivative with respect to x of this function f of x, or we could call that df dx, right? The rate of change of f over change in x. Then what we're going to get, by the chain rule, we take the derivative of the outside. The derivative of the tangent is the secant squared. So we get the derivative of the outside evaluated at the inside times the derivative of the inside. And the inside, in this case, is the secant of x squared plus 1. Now to find that derivative, that's going to require the chain rule again, because we've got x squared plus 1 inside the secant. So the derivative of the secant is the secant tangent. So we have all of this from the first time we applied the chain rule, and now we're getting the derivative of that original inside. The derivative of the secant is the secant tangent. So you get the derivative is secant of x squared plus 1 times the tangent of x squared plus 1, because it's the derivative of the outside evaluated to the inside, and the inside is x squared plus 1. So the derivative of the secant is secant x tangent x. You plug in the x squared plus 1 in both of those, and then finally you multiply by the derivative of that inside. Okay, but that derivative is pretty easy. Let me copy down everything we know so far, and then we'll just finish it off. The derivative of x squared plus 1, well, the derivative of x squared is 2x, the derivative of 1 is 0, so we just have 2x. So I think I'll do is I'll just copy that 2x out in front. I can multiply in any order, and it looks prettier to me to have that out there. Alright, here's another one. This looks pretty complicated, but again, it's just a quotient. We've got one function divided by another function. This is going to take a little bit of work, but because I can see to take the derivative of this, I've got a product, so I'm going to have to apply the product rule. Also, take the derivative of any of these pieces, that's going to require the chain rule, and that's going to require the chain rule. The derivative of the bottom is also going to require the chain rule. Well, let's just go through it step by step. The main thing is that I got one function divided by another function, so I should use the quotient rule, which says you take the derivative of the top. So I'm going to take the derivative of the top That's going to require a little bit of work, so let me just write out what I intend to do before I actually do it. The derivative of the top, I'm going to multiply that times the bottom, which is the natural log of the arctan of x, minus the top, which is e to the 2x times cosine x squared plus 1, times the derivative of the bottom, which is going to be the derivative of the natural log of the arctan of x, all over the bottom squared. So we've got the natural log of the arctan of x squared. Okay, now I just see that what I need to do is to figure out these two derivatives, and then I'll have it. So take the derivative of this first one. I'm going to take this is a product of two functions that I'm confident I can differentiate. So I'll apply the product rule. The product rule says that you take the derivative of the first times the second. Now the derivative of e to the 2x is just e to the 2x times the derivative of what's inside. That's just the chain rule there. The derivative of 2x with respect to x is 2. So we get e to the 2x times the derivative of what's inside, which is 2. It's because the derivative of e to some function is e to the function, right? And then the chain rule says you take the derivative of that function times that. Okay, so we got the derivative of the first times the second plus the first times the derivative of the second. The first is e to the 2x, and the derivative of cosine is negative sine. So we have the derivative of the outside evaluate the inside times the derivative of the inside, which is 2x. Okay, so far what I've calculated here is the derivative of the first, derivative of the top, basically, now times the bottom. We've got the natural log of the arctangent of x minus the top, this is coming from the quotient rule, times the derivative of the bottom. If you have the derivative of the natural log of a function, what you get is the derivative of the inside over the inside, because the derivative of the natural log is 1 over x. So you plug in the inside, you get 1 over the inside, then you multiply by the derivative of the inside from the chain rule. So the derivative of the inside, the derivative of the arctangent, is 1 over 1 plus x squared, all over the inside, which is the arctangent of x. So we have the derivative of the inside over the inside. Now we're done with that. Okay, so that was a little bit messy, but we got it done. We'll put some parentheses here to make sure you know that you're squaring the output of the natural log. Okay, it's a little bit messy, but we got it done. Now, one thing we'd probably like to do is to get rid of any tiny fractions within the larger fraction. Essentially, in this one, we've got an arctan in the denominator. And if we multiply this top and bottom by 1 plus x squared, we'd also have a 1 plus x squared in the bottom. So I think what I'll do is I'll multiply top and bottom by the arctan and by 1 plus x squared. So let's see, when we do that, we're going to have our natural log of arctan x all squared in the bottom, but now there's also going to be times 1 plus x squared and times the arctangent of x, because I multiply the bottom by that. If I multiply the top by that, then we get, let's see, from these, I'm going to go ahead and pull out that common e to the 2x. Okay, so I pull out the e to the 2x. Here I have 2 times the cosine of x squared plus 1 minus 2x times the sine of x squared plus 1 times the natural log of the arctan of x times 1 plus x squared times the arctan of x minus, now here when I multiply this by 1 plus x squared and by arctan, it cancels that fraction. So all we have left here is e to the 2x times the cosine of x squared plus 1. Now I've got rid of the complex fractions. At this point, it's looking to me that even if I could factor, there's not going to be anything to cancel with the denominator. So I'm going to give up. You could work on maybe looking for any like terms that might be common here, or expanding and collecting like terms and hoping to factor there. But I think we're pretty much stuck on this one, so I'm going to stop.